Swayam Prabha. Digital India. Educated India.
In the last two lectures, we discussed unconstrained optimization. Now, in this lecture, we will discuss the basic framework of constrained optimization. First, we discuss constraints. As I told you earlier, the typical form of an optimization problem is like this, in which you want to minimize a function of several variables in the vector x subject to certain inequality conditions and certain equality conditions. Conceptually, you can say that the statement of the problem is minimize function of x in which x must belong to a given domain omega. Now, the description of the domain can be made in terms of these constraints. Equality constraints constrain the feasible space to a lower dimensional set of the original solution space, as if you can talk of it as a surface in the three dimensional space. So, in the if the space of x is three dimensional, then one equality constraint like this will define a surface, and any point outside that surface will be deemed as infeasible. Inequality constraints do not reduce the dimension of the solution space, but they restrict certain regions of the solution space as infeasible. So, out of the three dimensional space, expressing inequality constraints as on this side of that wall of the room, on this side of this wall of the room, like that, we can restrain the feasible domain to this room rather than the entire infinite 3D space. So, when we have such constraints, you can talk of a tangent plane at every point on the surface describing the equality constraint. So, for equality constraint, if you have a surface, then at that point at that surface every point is feasible, and at that point you can talk of a tangent plane. So, how would you describe the tangent plane? So, for the vector function h in which the components are h1, h2, h3, etc., if you put their gradients like this, grad h1, grad h2, grad h3 and so on, and construct this entire matrix, which turns out to be basically the transpose of the Jacobian of h with respect to x. Then you can see that grad h1 will be the normal to the surface describing hx equal to h1x equal to 0. Similarly, grad h2 will give you a normal to the surface h2x equal to 0 and so on. So, what remains as the tangent plane will have directions which are perpendicular to all these gradient vectors, right. So, then before proceeding towards the theory of constraint optimization, we need to keep in mind one important point, is that in entire discussion that we make subsequently, it will be understood that grad h1, grad h2, all these are linearly independent. So, these columns are linearly independent. A point x which satisfies that condition is called a regular point, that is, and this condition, the linear independence of the gradients of the functions h1, h2, etc., that the property, the quality of that linear independence, that is called that condition is called constraint qualification. The idea of naming it as constraint qualification condition is that if at a particular point there are two constraints, but both of them have the same gradient or the gradients in the same direction, then that will mean that the tangent plane that is allowed by one of them is exactly the same as what is allowed by the other. Similarly, for the case of more than two such constraints and more than two such gradients, if it happens that they are linearly dependent, then that will mean that all the normals are not independent, all the normals to the surfaces are not independent. So, for that local neighborhood, the immediate first order region around that point, for that region, for that small region, one of the constraints could be dropped out. So, because they are not locally all independent. So, that is why when we say that all of these are linearly independent, then we mean that in the neighborhood, in the vicinity of that point, all these constraints really qualify as independent constraints. So, it makes sense to retain all of them. Otherwise, we could have dropped one of them for the local neighborhood. So, in all our theoretical discussion that we make subsequently, it will be understood that we are talking about regular points, where the constraint qualification condition is satisfied. Now, at such a point, at such a feasible point which is regular, we have already discussed that in the tangent plane, any direction is a direction which is perpendicular to or orthogonal to all the grad h1, grad h2, grad h3, etc. Right. So, these are the directions which are feasible directions, that is, along that direction you can make an infinitesimal movement without violating any of the constraints. If your movement has a component along the gradient of h, that means you are moving out of that surface, out of that tangent plane. So, that will be infeasible. So, this tangent plane, this subspace M consisting of those y's, those vectors, those directions which are orthogonal to all the grad h1, grad h2 vectors, they are the collection of feasible directions so far as the equality constraints are concerned. So, we find that if in a n variable problem in which at any point in the solution space there are n linearly independent directions possible, if there are k constraints, say if there are k constraints, then and all of them are locally independent, that is, they satisfy the constraint qualification condition, then on the vector y, on the feasible direction y, there will be k such conditions, that is, that y must be orthogonal to k different linearly independent vectors. So, if there are k such conditions, then the number of linearly independent vectors that can be taken as y will be n minus y, n minus k. So, n minus k linearly independent vectors can be there in the tangent plane. That way, you will find that from that point, if we want to conduct a search, we do not really need to conduct a search in the n dimensional space, because the tangent plane is n minus k dimensional, and in fact, all the k equality constraints together will define a manifold of dimension n minus k. So, that way you need to conduct the search on n minus k dimensional manifold, and the tangent plane is a planar entity of that many dimensions. So, that way you find that equality constraints reduce the dimension of the problem. So, that may be a positive thing, that may be something which is actually in a way reducing our job, but since in general the surfaces h x equal to 0, those surfaces are nonlinear, they are not all planar surfaces. So, that is why we will not be in a good position to take advantage of this reduction of dimension, because the satisfaction of the constraint itself will be a hindrance to remain on the feasible domain. However, there is a method called variable elimination method, which tries to use this fact and solve k of the variables in terms of the other n minus k variables, and then conducts the optimization process in that n minus k variables. That is possible only in case of very simple constraint surfaces, very simple constraint functions. However, so far as the tangent plane is concerned and the analysis of feasible directions in the tangent plane are concerned, effectively we keep in mind the concept of this elimination of certain direction and the restriction of the feasible direction set to a subspace or to a tangent plane. Now, what about inequality constraints? For inequality constraints, all of the inequality constraints need not be active at a point. For example, if this is an inequality constraint, say g1 x is less than or equal to 0. So, this is the feasible side, this is the infeasible side, that is g1 x is positive here, negative here, okay, and 0 on the boundary. Similarly, g2 x, similarly g3 x. So, you will find that at this point none of the constraints is active. Active in what sense? That is, in the immediate neighborhood of this point, whichever way we move, whichever way we try to displace the point, these constraints will not play a role. On the other hand, at this point g1 is called an active constraint, because from here there are some directions in which g1 is not violated. On the other hand, there are some directions along which g1 will be violated. So, g1 is an active constraint, g2, g3 are still inactive. At this point g1, g2 both are active constraints, g3 is inactive, and so on. So, when a particular constraint is active, that means the value of the corresponding constraint function is 0. That means, so far as that constraint is concerned, the point is on the boundary of the feasible domain. So, for the description of the tangent plane, we include the active inequality constraints in the list of the equality constraints only, okay. Because here if you try to work out the tangent plane, you will need to consider this, that is excluding this normal direction, because this will be the gradient direction, this will be actually the gradient direction, gradient of g1, okay. So, whatever we do for grad h1, grad h2, grad h3, same thing we will do for grad g1 here, but we will not do that for grad g2, grad g3, because they are inactive constraints. At this point these constraints are inactive. So, active inequality constraints get included among the equality constraints for the description of the tangent plane. That means, if an inequality constraint is active, that means the tangent plane gets its dimension reduced by one further value, one further dimension, okay. Apart from that, for inequality constraints, there is a concept of cone of feasible directions. In the case of an equality constraint, a point which is feasible, from that you cannot move along grad h, you cannot move along minus grad h. Both ways you will be leaving that constraint manifold, constraint surface, and going out of the feasible domain. On the other hand, for an inequality constraint, you cannot move along grad g, but you can move along negative grad g, because that way you will be coming to the interior of the domain, you will not leave the domain, okay. For example, at this point it is possible to move in all these directions. So, at this point if you try to draw two tangents like this and like this, this is tangent to g1, g1 equal to 0 surface, this is tangent to the boundary of g2. Now, in this entire zone all the directions are feasible, right. So, you find here that a cone like structure appears into picture, in which the directions are feasible, the opposite directions will not be feasible, okay. So, these directions will not be feasible, these will be feasible. Those directions which go towards the interior of the domain, leaving the constraint boundary, they will be feasible, and opposite ones will not be feasible. So, you define the cone of feasible directions in this manner. At that boundary point, the value of g is 0, and any direction that takes the x point towards a direction in which the g transpose d is negative will be all right, because g will become negative. So, now when we have to algorithmically handle the constraints, inequality constraints which are active and which are inactive, there are two possibilities of handling, two strategies to handle inequality constraints. their being active or inactive. One is active set strategy, in which at every iteration as we move from one point to another, a list of active constraints is maintained, and after every iteration we make a check regarding which of the active constraints has become inactive due to this particular step, and which other constraints which were earlier inactive have become active. So, this is called the active set strategy. At every iteration we make this update of active set. Active set update is basically in the form of a list, a set in which we enter the indices of the active constraints. There is another strategy called slack variable strategy, in which every inequality constraint like this is replaced with a corresponding equality constraint by addition of another variable which we call as the slack variable, with the condition that the slack this is equality, with the condition that the slack variable must be non-negative. So, we put a non-negative number here. So, if its value is positive, that means this constraint is inactive. If its value is 0, then this constraint is active. A negative value for the slack variable is not allowed, because that will make this constraint violated, that will violate this constraint. So, this is another strategy to handle inequality constraints, that is, which of them have to be taken in the active set and which are not. So, for that you do not need to maintain a list. The value of this will signify whether it is inactive or active. Now, with this understanding, we go to find out, we proceed to find out the optimality criteria for a nonlinear optimization problem in which there are constraints. So, for example, as we have been discussing, that for this corner point these directions are feasible, and any direction in the tangent plane is feasible, in a tangent plane is feasible. Now, if these are feasible directions, then what is the necessary condition for this point to be a local minimum point? The condition should be that along the feasible directions, if we make a move, then the function value should not decrease, because if along a feasible direction the function value can decrease, that will mean that the current point cannot be a local minimum. Okay. So, a direction along which the function decreases is a descent direction, and the direction along which we can move without violating any constraint is a feasible direction. So, for the point to be a local minimum point, it is necessary that there is no direction which is at the same time a feasible direction as well as a descent direction. So, if we can check that all the feasible directions are such that along that the function increases, the function does not decrease, then we will be satisfying the necessary condition for the point to be a local minimum. So, suppose x star is a regular point in which there are a few active inequality constraints and some inactive inequality constraints. Okay. And of course, equality constraints are always active. So, we collect all the active constraints, grad h full and grad g only the active part, and then we say that grad h1, grad h2, grad h3, and out of this also gradients of the active inequality constraint functions we collect. Now, these gradients together, which are all linearly independent because they satisfy the constraint qualification condition. So, all these together will be those vectors to which a tangent plane vector must be orthogonal, right. So, this collection of gradient vectors is the full set of linearly independent vectors which must be orthogonal to any vector in the tangent plane. So, therefore, these together, these columns together give us a basis for the orthogonal complement of the tangent plane. If tangent plane is this, then whichever subspace which is orthogonal to it and completes the Rn full vector space, then that is the orthogonal complement of the tangent plane for which these gradient vectors together offer a basis. For the tangent plane also we can work out a basis. suppose that basis is D having these many vectors. Okay. In this case, we described n minus k as the dimension of the tangent plane, but in this notation here actually the number of constraints is n minus k and dimension of the tangent manifold tangent plane is k. So, if we think of a basis for the tangent plane itself, then this basis for the tangent plane and this basis for the orthogonal complement of it, that is what is perpendicular to the tangent plane, together gives us a basis for R n, that is full n dimensional space. Now, x is an n dimensional vector. So, in the space of x, any vector is an n dimensional vector. In particular, gradient of f is also an n dimensional vector. So, it can be expressed in this basis. So, if we try to do that, the negative gradient is a vector in R n. So, we try to express that in this basis. One part of it describes the tangent plane and the other part describes all orthogonal vectors. Now, we say that dz is the component of negative gradient in the tangent plane and these two together is component of the negative gradient orthogonal to the tangent plane. Okay. So, if this is the tangent plane, then at this point, if this is negative gradient, then you would say that this vector is dz, that is component of the negative gradient in the tangent plane, and this vector is the rest of it. Right. Now, if this is non-zero, say positive or negative this way. So, along all the directions d1, d2, d3, d4, positive or negative whatever, if this is non-zero component, then you see that this is tangent plane in which every direction is feasible. Okay. In the tangent plane every direction is feasible. Now, if negative gradient has a non-zero component in this tangent plane, then moving in that direction we should be able to reduce the value of the function, right. So, then this point cannot be a local minimum point, because along this direction which is feasible we can have a positive component of negative gradient, okay, and we can reduce the function value along this direction. So, that is why for this point to be a local minimum point, it is necessary that the negative gradient vector has no non-zero component in the tangent plane. That means z must be 0. So, this is what we can say if x star, this current point, is a solution to the nonlinear programming problem, the nonlinear optimization problem, minimize f subject to those constraints. So, this is what we can say about the components z lambda mu. Okay. Out of that we can say that z cannot be non-zero if x star is a solution to the problem, solution to the minimization problem. So, components of gradient of f in the tangent plane must be 0, z is 0. So, that means this negative gradient cannot have a component in the tangent plane and it must be orthogonal to the tangent plane. That means the negative gradient should be completely describable in terms of the normal vectors, gradient vectors of h1, h2, h3, etc., and active fellows from here, active members from here. Okay. Now, what else we can say? Now, this is going to be a little complicated, keeping track of active constraints, because suppose in a particular problem there are say 7 constraints. Okay. So, at a particular point, suppose this is active and this is active. So, at that particular point you will be taking g1, g2, g4 and assembling them in this vector g active, and G3, G5, G6, G7 you will be assembling in G inactive. At another point when you analyze, suppose there G4 is not active, but G7 and G6 are active. So, then again you will be reassembling this all part. So, this problem is typically handled by saying that we will keep all the gradients here and all the G's we will consider together, except that, and that way if we keep rather than 3, if we keep 7 columns here, then mu will have 7 values. Okay. So, we will say that let it have 7 values, but we will insist that if a particular constraint is inactive, the corresponding mu should be 0. Okay. So, if G1, G2, G6, G7 are active, then mu1, mu2, mu6, mu7 can be non-zero, G3, G4, G5 must be 0, mu1, mu2, mu3, mu4, mu5 must be 0. That is corresponding to those constraints which are inactive, let the columns stay in their place, but corresponding mu's we will insist on being 0. If we follow that kind of an understanding, that is for inactive constraints the corresponding mu's should be 0, then rather than having only active constraints here, we can put active inactive constraints in any order for that matter, and say that inactive constraints will have the corresponding mu's which are 0 anyway, so that they do not affect this expression. Okay. So, extra columns will be there, but their corresponding multipliers will be 0. So, that way we can keep the entire G together, and this long thing we can concisely write as grad H lambda plus grad G mu, with the understanding that those mu's which correspond to inactive constraints will be 0 anyway. Okay. And that gives us this requirement, that is, if a particular constraint is inactive, then the corresponding Gi is not 0. So, the mu I has to be 0. On the other hand, for an active constraint, Gi itself is 0. So, mu I can be allowed to be non-zero. So, mu I Gi, the product is always 0. So, that is called the complementarity condition, that is between mu and G, for each I the pair mu I and Gi are complementary to each other. If one of them is non-zero, the other one must be 0. So, together you can write like this also, that is the sum of mu I Gi is also 0. Okay. Now, this condition we arrived at from here, in which we say that the negative gradient is a combination of grad H lambda and grad G mu only, dz part is 0. So, based on that we arrived at this condition. Just take this negative gradient on the other side, it goes as positive, and this is the first order necessary condition arrived from the requirement that along the feasible directions in the tangent plane there should be no scope of improvement of the function value. What about the directions in the cone of feasible directions? When we explore that, we say that now take this itself. Okay. Now, take this itself in another schematic diagram. Now that you have already decided that grad f will have no component in the tangent plane, then let us expand this part itself, which is the direction, which is the component in the direction normal to the tangent plane, and resolve these two parts. For this subspace only, now if we draw directions, and this is the direction of grad H and this is the direction of grad Ga, and we are currently at this point. Okay. Now, in this along this and these directions, the negative gradient can have a component. So, if the negative gradient is this way, now that means that the negative gradient will have one component along this, which is grad H into lambda, and another component along this, which is grad Ga into mu. Now, let us remove everything else to make this thing clearly visible. Now note that grad h is a direction along which if you move, then you will be leaving the constraint manifold, and constraint surface you will be leaving and going out. Okay. Similarly, if you try to move in this direction rather than this way and this way, either way you move out of the constraint manifold in the direction of grad h or in the direction minus grad h, that means that constraint manifold you are going to leave, you are leaving tangent plane and going out of the surface this way or going out of the surface this way. So therefore, minus grad f having a component along gradient of h or its negative will not be a problem, because this direction is anyway infeasible. So the condition for this point for to be a local minimum is that along a feasible direction we should not be able to reduce the function value. In this direction function value does reduce, but that is not feasible. Similarly, along this direction, if the grad f had a component in this direction, that is if grad f were like this, then it would have a component along this direction. In that case, the function would be reduced in this direction, but this direction is not feasible. So this is the case with lambda h, therefore grad h. So therefore lambda could be positive or negative. So negative gradient can have a positive component along grad h or a negative component along grad h, it does not matter. But consider the situation with grad g. At this point, since g is an active constraint, that means the value of g is 0 here. Okay. This is the direction of grad g, that means here it is positive, here it is negative. Now if the negative gradient has a component along this direction, that means along this direction it is possible to reduce the function value, because negative gradient has a component along this direction. But that does not harm, that does not stop this point from being a local minimum, because this is a direction in which even if the function value does decrease, it does not matter, because that direction is not feasible. In this direction g will become positive, grad g is in this direction, g is 0 here, g is positive here. On the other hand, if minus grad f is like this, having a component along negative grad g, that is in the grad g direction, if it has a negative component, that means it is feasible. This at this point g is 0, in this direction g will become negative, that means the point will be feasible, the constraint will be satisfied. So this point is feasible. So if negative grad g, negative gradient of the function minus grad f has a component in this direction, that is has a negative component along grad g, then this point cannot be local minimum, because since it is a component of minus gradient, negative gradient of the function, along this direction function could be decreased, and if this is a direction which is in the direction of negative gradient of g as well, that means it is feasible. That means this direction will be feasible direction and descent direction at the same time, a feasible direction in which the function value can be decreased. So if that happens, then this point cannot be a local minimum. So that means for this point to be a local minimum, the components along the negative gradient of inequality constraints must be positive. That is, this is allowed, but this is not allowed. Okay. So mu cannot be negative. This is what we get when we consider the feasible directions in the cone described by the active inequality constraints. So negative gradient can have no component towards decreasing g. Okay. That means mu's should be all non-negative. Okay. So corresponding to active constraints, mu should be non-negative, and for the inactive constraints we already know that they are all 0. So together we can write this. Okay. So all the conditions that we have collected till now, if we summarize, then we get what is called the first order necessary conditions or KKT conditions, Karush-Kundukar conditions, and the summary is this: if x star is a regular point of the constraints and a solution to the optimization problem, minimize f subject to g less than equal to 0 and h equal to 0, then there exist lambdas and mu's, that is Lagrange multiplier vectors, such that this and this, that is grad f plus grad h lambda plus grad g mu is 0 with mu non-negative, which comes from optimality requirement. And from the feasibility requirement, which is part of the problem statement itself, that is h x star is 0 and g x star is negative or 0, and complementary condition is this. This condition could as well be written as that is for all I, mu I g I at x star should be 0, that is complementarity condition, that is mu's and g's are complementary to each other, that is if g is non-zero then mu must be 0, that is for inactive constraints, and if mu is non-zero then g must be 0, that is mu can be non-zero only for active constraints. Okay. So, that is why this is called complementarity conditions. So, you find that here you have got n equations, number of variables, here you have got another bunch of equations, number of equality constraints, and here you have got another bunch of equations which is the number of inequality constraints. Same number of unknowns you have, in x you have the number of unknowns which is equal to n, the dimension of the problem, and you have got that many lambdas as many equations here, and you have got that many mu's as many equations here. Okay. So, the number of equations this and the number of unknowns x lambda mu is same. Apart from that, there are a few inequalities, mu's are greater than 0, g's are less than equal to 0. So, any point x star with suitable lambdas and mu's that satisfy all these inequality and equality requirements, they are said to be, those points are said to be KKT points or Karush-Kundukar points. So, that means they satisfy the first order necessary conditions. That does not mean that they are local minima, that only means that if a point is local minimum, then that satisfies all these conditions with some suitable lambda mu values. There is one class of problems called convex programming problems, in which the objective function is convex and the domain is also convex, characterized by convex GIs and linear edges, that is equality constraint functions are linear and inequality constraint functions are all convex. So, that describes a convex domain. So, if you are trying to minimize a convex function in a convex domain, then that is if your problem is a convex programming problem, then these KKT conditions are not only necessary, but also sufficient. But for a general problem, these are not sufficient. For a general problem, you need to consider the second order conditions also to be certain that a point satisfying these constraint conditions is a local minimum point. So, the second order condition is a little complicated. We will just make a brief overview of it and try to understand what it means rather than going into the detailed derivation. And before that, we define what is called the Lagrangian function. This function described in with the help of the objective function, the constraint functions from equality constraints and inequality constraints along with the Lagrange multipliers, lambdas and mu's. This function is called the Lagrangian of the problem, and this is why these lambdas and mu's are called Lagrange multipliers corresponding to equality constraints and inequality constraints. Okay. So, you will find that the first order optimality conditions that we worked out, this equal to 0, this is essentially the gradient of this with respect to x. You see gradient of f plus grad h lambda plus grad g mu, that is what we had here. Okay. So, gradient of lambda equal to 0 is the optimality condition. So, necessary condition for a stationary point of the Lagrangian also would be the same, that is this, and derivative with respect to lambda will be actually given like this, which will be nothing but h x equal to 0. That is the feasibility condition, equality condition itself, equality constraint itself. Now, the idea of the second order necessary and sufficient conditions is essentially the analysis of the second order change in the tangent plane. Okay. So, we again resurrect the tangent plane discussion that we had earlier. If this is the tangent plane, then our previous discussion tells us that minus grad f must be perpendicular to it, must be orthogonal to it, okay, because a component of negative gradient along the tangent plane would give us a first order change along the tangent plane, which means that we could decrease the function along the tangent plane along a feasible direction. So, since that is not allowed, we are already sure that negative gradient of the function must be orthogonal to the tangent plane. So, that means along the tangent plane from this point there will be no possibility of a first order decrease, okay, no first order change, because first order change of the function value in the tangent plane is 0 around this point. What about the second order change? So, as you know, the second order change is given by this, okay. So, when we try to analyze the second order change, we say that we do not care if there is a second order change which is in this direction or in this direction, because in these directions we have already completed the first order analysis, okay, and these points are, these directions are anyway not feasible. So, for grad h, say this can have a component along grad h and a grad g for that matter. So, along grad h this movement itself is not feasible, so we do not bother about that. Along grad g movement is feasible in one direction, but along that direction, since mu itself is positive, that means the first order change itself is positive. So, that means the first order term dominating the Taylor series will not leave any scope for the second order change to be perceptible in the immediate neighborhood. So, the second order analysis we need to conduct only on the tangent plane. Then we say that if we take a small movement, small move, if we make a small move along the tangent plane, then how the function value is going to change up to second order level. First order change along tangent plane is 0 anyway. So, what is the second order change? If that second order change is non negative, then we say that is the condition, that is the necessary condition for the current point to be a local minimum point. On the other hand, if the second order change is positive, then we would say that it is sufficient to ensure, along with the KKT conditions, it would be sufficient to ensure that the current point is a local minimum point. So, necessary condition and sufficient condition will be the same as the positive semi definite and positive definite nature of this Hessian matrix, but not in all directions, only on the tangent plane. That means the Hessian should be in, now here the Hessian that would be involved, and that actually is the result of a little complicated analysis which we are omitting. The Hessian that will get involved here is actually not the Hessian of the original function, the objective function, but Hessian of the Lagrangian. So, we say that the effect of the Hessian of the Lagrangian on the tangent plane should be like a positive definite matrix. Be outside the tangent plane, that is normal to the tangent plane, even if it displays a negative eigenvalue, that does not harm. So, that means the condition is that the Hessian matrix of the Lagrangian function is positive semi definite on the tangent plane M, orthogonal to the tangent plane, even if it does not behave in a positive semi definite fashion, even if it behaves with an indefiniteness, it does not matter. The only requirement is on the tangent plane. So, this is necessary condition. positive semi definiteness of the restriction of Hessian on the tangent plane. Okay. Sufficient condition is that it is positive definite. Okay. So, if we want to analyze that a Hessian matrix is positive definite on a particular subspace, then for that we can construct this matrix. That is, if D is an orthonormal basis of the tangent plane and HL is the Hessian of the Lagrangian function, then D transpose HLD will be a mapping, will be a symmetric mapping within the tangent plane, that is, it maps the tangent plane to itself. Okay. And we can examine the positive definiteness of this matrix, which is smaller, n minus m by n minus m. The other subspace, the orthogonal complementary subspace of m dimensions, is removed out of it. So, we can consider the positive definiteness of this. So, this is the second order condition. So, along with KKT condition, this being positive definite is sufficient for the current point to be a local minimum for all problems, even for non convex problems. Now, long back in the first lecture of on optimization, I mentioned to you that at the beginning of the optimization process, some of the variables of the problem can be considered constant for the analysis and frozen. Those are called the parameters. After the solution is found, typically we would like to examine whether freezing their values was a good idea. That is, we would like to examine the sensitivity of the solution to those parameters. So, how do we analyze the sensitivity? Consider this NLP problem, nonlinear programming problem. For simplicity, I have kept only equality constraints and not inequality constraints, but the theme applies for inequality constraints also. Again, for simplicity, I have considered only one parameter, which is kept fixed. Now, suppose for solving this problem, in the beginning we assigned a value to p and then solved the problem, and then we got the solution as x star, okay, a point in the solution space, and the corresponding function value. Okay. Now, note this, when we find the function value, we find it at that x star, which means that with that constant value of p, which we froze in the beginning. Consider another important issue, that as we gave a particular value, as we assigned a particular value to p, we got this optimal point, we got this minimum point. If we had given another value of p, we would have got a different minimum point. If we had continuously varied p, that is p equal to 1, p equal to 1.01, p equal to 1.02, p equal to 1.03, then continuously we would get some x star, some other x star, some other x star, some other x star. That way we can consider that this x star is actually a function of the p that we give, right. Here, as variables of the problem, x and p are independent variables, but x star is the optimum point which has been arrived at through a long process of optimization after assigning the value of p. So, as we keep on changing the value of p, the resulting optimal point will keep on changing. So, that way x star is actually a function of p. And therefore, when we finally evaluate the function, we will be actually evaluating this, right. Now, we want to find out if we change p a little bit, then how this would change, or more importantly how the corresponding function value would change, which we want to minimize. That is, we want to find out df by dp. At what rate the change of p affects the change of f. Okay. You know how to find the total derivatives of this kind of functions. F will depend on p in two ways, one directly and the other through x star p. Okay. So, the total derivative would be this partial derivative plus the derivative reflecting the dependence through x star, dependence on p through x star. So, that will be grad f, that is derivative with respect to x multiplied with how x star itself changes with p, this, right. Now, given the function here, it would not be difficult for you to find out this, but then how to find out this? Yes, you could solve the same optimization problem for another p and then get this, but there is a simpler way to solve for it, and for that you note this h x p equal to 0. At the solution point x star p, this is satisfied, right. If you make a small difference, small change in p and then solve the entire problem, then you will get another x star p which will also satisfy the new h corresponding to the new value of p. Okay. That means, whatever changes in p you made, h of x p still remains 0, because it will be the new x star will be feasible with respect to the new h defined with the help of the new p, right. So, this will be still satisfied. That means, as you change p, h remains 0. That means, dh by dp of this is 0 always. So, that will mean 0 equal to derivative of this we construct in this same manner. And now, what you can do is that multiply this lower equation with lambda and add to the upper equation. On this side, 0 will be multiplied with lambda and added to this. That means, on the left side there will be no change. On the right side there will be some change. What will be that change? Lambda into this will be added here, and here what will be added? Dx star by dp is constant, is common. Here will be added grad f plus lambda grad h. Okay. So, grad f plus lambda grad h is the first order necessary condition for the point x star to be minimum. Okay. That equal to 0 is the condition. That means, lambda times this added to this will make it 0. Okay. And lambda times this added to this will make it grad f plus lambda grad h, that is del f by del p plus lambda del h by del p. So, here you find that analyzing the sensitivity is actually not that difficult. So, you can construct these partial derivatives from the given functions and analyze the sensitivity of the problem of the solution to the parameter p. These things, when formalized in terms of large number of constraints and large number of parameters, give you these long conditions. Similarly, you can check the sensitivity, you can examine the sensitivity with respect to constraints also, and if you do that, then you find the sensitivity of the functions of the solutions to the constraints is just given by lambda mu, and that way you can say that the Lagrange multipliers lambda and mu signify costs of pulling the minimum point in order to satisfy the constraints. That is, lambda and mu Lagrange multipliers are costs for satisfying the constraints. Beyond this, we will discuss in the next lecture, in which we will consider duality and study the structure of nonlinear optimization methods. Thank you.